Okay, in the previous class, we were solving the second problem on unsymmetric I section, correct? Let me glance the things which I covered in the previous class and let me go ahead with the remaining portion of the problem. Okay. An unsymmetrical I section beam is used to support an imposed load of 2 kN per meter over a span of 8 meter. The lay load on the beam is 2 kN per meter and the length of the beam is 8 meter. The sectional dimensions of the I section are given: flange width, okay, and web thickness, flange thickness. Every data required for the sectional dimensions are given. Then prestressing force is given as 100 kilonewton, and it is located at a distance of 50 mm from the summit of the beam. That also we have written here in the diagram. Then it is asked to find the resultant stresses, which includes the combination of prestress and the sulfate. And the second question is resultant stresses with respect to the combination of prestress, sulfate, and the live load. Okay, this was the question. Part of the problem we have solved. Okay, in that what we have done is initially we have written all the given data. Then the area of the cross section, total area of the cross section we have determined. We got it as 46,400 mm square. Then we have also determined the distance of centroid from the bottom fiber. Distance of the centroid from the bottom fiber also we have determined. Okay. So continuing the solution, we got the answer for distance of centroid from the bottom fiber YB. We got how much we got? We got it as 244 mm. 244 mm from the bottom fiber. From the bottom fiber. So the distance of the centroid is at a distance of 244 mm. Let me mention it in the diagram. Okay. Let me mention it in the diagram. If we assume centroid of the I section at this point G, so YB is how much? Distance of centroid from the bottom fiber is 244 mm. 244 mm. Okay. So if you know the distance of centroid from the bottom fiber, you can easily find distance of the centroid from the top fiber. How you can find? Overall depth minus this YB will give Okay, sorry students, we will continue the class. It was an office call. So we got distance of centroid from the bottom fiber. Okay. If you know the distance of centroid from the bottom fiber, you can easily find distance of centroid from the top fiber. Okay. So how we can find is total depth, overall depth minus this 244. If you do, you will get distance of centroid from the, write the G here. Already I have written centroidal axis. Okay. G YB. You can easily find YT. YT represents distance of centroid of section from top fiber. Okay. And that YT will be equal to 400 minus YB. That is 244. YT is equal to, therefore YT is equal to 400 minus 244. If you do, you will get the answer as 156 mm. You will get the answer as 156 mm. Okay. Now YT is equal to 156. Here YT is equal to 156 mm. Okay. So here YT distance of centroid from top fiber. Distance of centroid from top fiber. Okay, distance of centroid from top fiber. Okay. Now this is the first step. Next step is to find the eccentricity. If you locate the centroid, then you can easily find the eccentricity. What is eccentricity? Eccentricity is the distance between the centroidal axis to that of the point where the prestressing force is applied. Okay, the point where the prestressing force is located. That is called as eccentricity. That eccentricity you can easily find now. Correct? Let me show the eccentricity here. Eccentricity will be from here to here. So this is what the eccentricity. Now you can easily find eccentricity now. Okay, that eccentricity is the distance between centroidal axis to the top point where the prestressing force is applied. Point where the prestressing force is applied. Okay. That eccentricity, how you can find it? So you know YB, correct? You know YB, distance of centroid from the bottom fiber. And distance of prestressing force from the bottom fiber is how much? It is 50 m. Here I written. Okay. That YB minus 50, if you do, you will get the eccentricity. Correct? YB minus 50, if you do, you will get the eccentricity. Below you write distance of centroid. Distance of, therefore, distance of centroid from, sorry, eccentricity therefore eccentricity E is equal to 244 minus 50, that is YB minus 50. If you calculate this answer, it will be 194 millimeter. 194 millimeter. Okay, therefore E is equal to 194 millimeter. Okay. This eccentricity is required for calculation of the stresses, correct? Now force P is known, 100 kilonewton. Area of section is calculated, that is 46,400 mm square. The eccentricity is calculated. Okay. Then what else is required? We have to calculate section modulus also, correct? Now section modulus. To calculate section modulus, you should know moment of inertia. Moment of inertia I. Okay, because section modulus Z is equal to I by Y. Okay. So we will calculate moment of inertia initially. Then using that moment of the inertia I, we can calculate the section modulus Z. Okay. Now moment of inertia. Moment of inertia I xx is equal to moment of inertia about x axis is equal to, what is the formula for moment of inertia? It is I g g plus a into h square is the formula. Okay, igg plus a into h square, where igg is moment of inertia of individual component at about its own centroidal axis. Okay, igg represents moment of inertia of each and individual component about its own centroidal axis, and a is corresponding area of each element, and h represents distance between the centroid of whole figure to that of centroid of individual figure. Okay, distance between centroid of whole figure to that of centroid of individual figure represents the h. Okay, we will calculate now. So here we have the I section. This whole I section is divided into three components, 1, 2, 3. Okay, and each and every section are rectangle only. Therefore, moment of inertia for rectangle is what? Igg is equal to, it is BDQ by 12. BDQ by 12. Correct? BDQ by 12. Now, A1. Here we have three components. For all the three components, we have to individually calculate area and H value. Area and H value. Initially, we will calculate for rectangle 1. For rectangle 1, A1 is equal to A1 is equal to A1 is equal to rectangle 1, A1 is equal to 100 by 60. Correct? 100 into 60. 100 into 60, that is 6000 mm square. Okay. Then H1 you need to calculate. Correct? H1 will be equal to, as I said, H1 is distance between centroid of whole figure to that of centroid of individual component. We are doing the calculation for member 1 or component 1. Okay. So if I assume distance of the centroid of rectangle 1 as G1, total is 60, no? So at G1, okay? G1, centroid of rectangle 1, if I assume as G1, distance between G1 and the capital G represents H1. Okay, I hope you are understanding. Distance between centroid of rectangle 1 to that of centroid of whole figure will be H1. Okay, how you will calculate that? From bottom fiber, distance of centroid of rectangle 1 will be at a distance of 30 mm. That is 60 divided by 2, 30. Okay, so that 244 YB 244 minus that 30 will give distance between both G1 and G. Okay, therefore H1 is equal to 244 minus 60 by 2. Minus 60 by 2 means 30 minus 30. What is the answer? It will be 214 millimeter. 214 millimeter. Then you calculate area 2. Okay. Area of rectangle 2. Area of rectangle 2 is 80 mm is the width. 280 mm is the depth. So 80 by 280. 80 by 280. So it will be how much? 22,400 mm square. Okay, so here we have already calculated, no? A1, A2, A3. So same value I'm writing here. Then H2 will be equal to what? H2 will be equal to distance between centered of rectangle 2 and the centered of the whole figure. Distance between centered of rectangle 2 and the centered of the whole figure. If I assume G2 as centered of rectangle 2, okay? So distance between capital G and G2 will be H2. Okay, it will be H2. Now how to find that? How to find this distance H2? How will find? From the base, okay, distance of centered of whole figure is 244 mm. Okay, similarly, from the base, distance of centered of rectangle 2 will be 60 plus 280 divided by 2. Okay, 60 plus 280 divided by 2. Therefore, the H2 will be equal to 244 244, okay, that is distance of centered of whole figure from the base minus distance of centroid of rectangle 2 from the base. Okay, distance of centroid of rectangle 2 from the base will be equal to 60 plus depth divided by 2. 60 plus 280 divided by 2. Okay, 60 plus 280 by 2. 60 plus 280 by 2. If you do, you will get H2. How much it will be? So if you calculate, so answer is 44 mm. Please cross check the answer. All of you please solve by your own and get the answers and cross check the answers which I am writing here. Okay. Then similarly, you need to perform the calculation for component 3, that is A3. A3 is what? A3 is equal to, it is 300 into 60. How much we got here? 18,000. Correct? 300 into 60. 18,000 mm square. Then H3 will be equal to how much? H3 is nothing but distance between centered of rectangle 3. Okay. Let me take distance of centered of rectangle 3 as G3. Distance between this G3 and G will give H3. Distance between G3 and capital G will give H3. How will calculate? First you calculate distance of centroid of rectangle 3 from the base. How much it will be? It will be 60 plus 280 plus 60 divided by 2 minus y bar, that is 244, will give distance between both G3 and capital G3. Okay, therefore I'll write the same calculation here. 60 plus 280 plus 60 by 2 minus 244, okay, is equal to 126 mm. 126 mm. Okay, therefore the moment of inertia Ixx is equal to you can find the moment of inertia now. So moment of inertia of rectangle is BDQ by 12. For rectangle 1, B is 100, depth is 60. So 100 into 60 cube by 12. 100 into 60 cube by 12 plus AH bar square. AH square is there, no? A1 H1 square. Okay. A1 is 6,000. 6,000 into 214 square. For rectangle 1, it is over. Similarly, calculate for rectangle 2. For rectangle 2, BDQ by 12. B is 80. Depth is 280. 80 is the width. 280 is the depth. BDQ by 12. 80 into 280Q by 12 plus AH2 square. A2H2 square. A2 is 22,400 into H2 is 44 square. This is the calculation for rectangle 2. For rectangle 3, BDQ by 12, that is 300 is the width, 60 is the depth. 300 into 60 cube by 12 plus 18,000 into H3 square, 126 square. So this will give moment of inertia of the I section about its centroidal axis XX. Okay, therefore I is equal to moment of inertia. I is equal to, if you calculate the answer, you will get 757.45 into 10 power 6 mm4. Okay, if you want, we can calculate. Moment of inertia will be 757.45 into 10 power 6 mm raised to 4. Cross check the answer after the calculation. Therefore, if you know the moment of inertia, you can easily calculate section modulus. Okay, section modulus ZT and ZB. Okay, here I said that in the previous class only I have said the distance of centroid from bottom fiber and top fiber, it is different. Okay, if it is a symmetric about x-axis, then ZT equal to ZP is equal to Z. Okay, but it is not symmetric about x-axis. Therefore, you need to individually calculate ZT and ZB. Okay, therefore, ZT is equal to I by YT. Okay, I is 757.45 into 10 power 6 divided by YT is how much? We got it as YT, we got it as 156 mm. 156 mm. So section modulus about top fiber is 4.855 into 10 power 6 mm cube. Okay. Similarly, you can calculate ZB, section modulus about the bottom fiber. What will be the formula? It will be I by YB. It will be I by YB. Same moment of inertia 757.45 into 10 power 6 divided by YB is 244. The answer is 3.104 into 10 power 6 mm cube. Okay. So to this you got ZB. Okay. Z values, section modulus values you got now. What next after finding these things? See, you got, prestressing force, cross-sectional area, the eccentricity, then you have calculated section modulus. What else is required for the calculation of the resultant stresses? You require moment due to sulfate. You also require moment due to live load. That we will calculate now. Okay. So to calculate moment due to sulfate, you write the side line as moment due to sulfate. Moment due to sulfate. Moment due to sulfate, that is Mg. Okay. First you calculate the sulfate of the section. So we know the total area of the section. Area of cross section is how much? Total area we have calculated before now. How much we got there? Total area. It is 46,400 mm square. Correct? 46,400 mm square. But while calculating the sulfate, we should have the answer in terms of meter square. You convert this into meter square. 46,400 into 1 mm is equal to 10 power minus 3 meter whole square. Okay, the answer will be 0.0464 meter square area of cross section A. Now you can calculate the sulfate. Therefore sulfate Okay, sulfate is equal to Wg is equal to cross sectional area into density cross sectional area into density. Cross sectional area is 0.0464 into density is 24 kilonewton per meter cube. Okay, it is given in the problem, I think. Correct now? Density of the concrete. Even if it is not given, you need to remember. You need to remember the value. I think it is not given in the problem. Yes. You need to remember it is a standard value. The density of the concrete is 24 kilonewton per meter cube. Okay. Here I am right in the bracket. Density of concrete 24 kilonewton per meter cube. So what is the answer that you get? Wg is equal to, if you calculate the answer, you will get 1.12 kilonewton per meter. 1.12 kilonewton per meter. Okay. Therefore, if you know the sulfate, you can calculate sulfate moment. Therefore, mg moment due to sulfate is equal to Wg L square by 8. Okay. Length of the member is given as 8 meter. Therefore, it is 1.12 into 8 square divided by 8. Mg is equal to 8.96 into 10 power 6 Newton millimeter. 8.96 into 10 power 6 Newton millimeter. Okay, this is moment due to sulfate. Okay. Similarly, you calculate moment due to live load. Moment due to live load. Moment due to live load. Moment due to live load is represented by MQ. Okay. So moment due to live load is equal to WQ L square by 8. Live load on the beam is given. Correct? Live load on the beam. How much it is given? Imposed load of 2 kilonewton per meter. Okay, 2 kilonewton per meter is the live load which is acting on the beam. Okay, live load WQ is given as 2 kilonewton per meter. Therefore, MQ is equal to 2 into 8 square by 8. What is the answer? I think 16. MQ is equal to 16 kilonewton meter, or 16 into 10 power 6 Newton millimeter. Okay. Let me write this moment due to sulfate. Okay, in terms of Newton per millimeter only. I written the answer. Okay. So you will get 8.96 kilonewton meter in terms of Newton per millimeter into 10 power 6 Newton millimeter. Okay. Now, I think we got all the required parameters to calculate the resultant stresses. Okay. We know the pre-stressing force P, area of cross section is known, eccentricity is known, section modulus is known, moment due to sulfate is known, moment due to live load is known. Now you can calculate the resultant stresses with respect to the given conditions. There are two conditions given in the problem. Okay, what are those conditions? We have to find resultant stresses for the combination of pre-stress and the sulfate. That's the first question. Second question is to find the resultant stresses for the combination of pre-stress, sulfate and the live load. Okay. So for easy calculation, you make a tabular column. First, you write type of stress, Then so we need to calculate the stresses at top fiber and bottom fiber, no? So you make two columns again at the top fiber, unit will be Newton per mm square. Then at bottom fiber also we need the stresses fiber. So answer will be in terms of Newton per mm square. Okay. Now we will write one by one. There are two main kinds of stresses. Okay. Three main kinds of stresses. I'll go to the figure again. There is direct stress due to prestressing force and bending stress due to prestressing force, sulfate, and stress due to layer load. Three main kinds of stresses in prestress, again two different types. Okay. Now I'll take each and individual type of stresses separately in this tabular column. First one is pre-stressors or pre-stress. First one is pre-stress. Pre-stress. Okay. So how to calculate the pre-stress? Pre-stress is calculated as P by A. Correct? Direct stress due to pre-stress P by A and bending stress due to pre-stressing force is calculated as P by Z. Okay. I'll write the same formula here. Okay. There are two kinds of stresses to be calculated. One is direct stress, which is calculated as P by A. Second one is bending stress, which is calculated as PE by ZT. Okay. So with respect to top fiber, you need to substitute the section modulus with respect to the top fiber only. With respect to the bottom fiber, the formula will be PE by ZB. Then coming to the sign convention, it will be same only. See here you can see at bottom fiber positive sign, at top fiber negative sign. For direct stress it is plus P by A plus P by A for both the top and bottom. For bending stress due to prestressing force, top fiber is having negative, bottom fiber is having positive sign. I will give the same sign here. The top fiber is having negative sign, bottom fiber is having positive sign plus P by ZB. Okay. So P, the prestressing force P, how much it is given? 100 kilonewton. 100 kilonewton is 100 into 10 power 3 divided by overall cross sectional area of the section is how much? 46,400. If you calculate the answer, it will be 2.15 Newton per mm square. Then minus P by ZT minus 100 into 10 power 3 into eccentricity. How much we got? Eccentricity. At the beginning only we have calculated the eccentricity. It is 194 mm. 194 mm into 194 divided by ZT. ZT is how much? ZT 4.855 into 10 power 6. 4.855 into 10 power 6. Okay. So answer, if you calculate, it will be minus 4. Similarly, P by A will have the same answer, plus 2.5 only. Plus 2.5. Then plus P by ZB, it will be plus 100 into 10 power 3 into eccentricity 194 divided by ZB value is how much? 3.104 into 10 power 6. 3.104 into 10 power 6. So answer, if you calculate, it is plus 6.25, plus 6.25. Okay. Now first type of stresses is over. That is stresses due to pre-stressing force is over. What is the next type of stress? Self-weight stress is there, live load stress is there. Okay, we will calculate now. Second one, self-weight stress. Second one, self-weight stress. Okay, self-weight stress, how it is calculated? What is the formula? It will be, and if you refer the sign convention for self-weight, the top fiber having positive sign, bottom fiber is having negative sign. Okay, so here for top fiber plus mg by z top zt. Okay, here minus mg by zb, minus mg by zb. So mg is how much? Mg 8.96 into 10 power 6, 8.96 into 10 power 6 divided by ZT 4.855 into 10 power 6. Answer is 1.84 plus 1.84. Check the answer. If you get any other different answer, let me know. Here mg is same, minus z, minus 8.96 into 10 power 6 divided by zb is 3.104 into 10 power 6. Answer is minus 2.89 Newton per mm square. Okay, to this self-weight stress is over. The last type of stress what we have is live load stress. Live load stress. Okay, the sign convention for live load stress is same as self-weight stress. You can see here in the figure. Plus top fiber minus bottom fiber. Only in place of mg, mq will come into picture. Moment due to live load. Okay, plus mq by zt. Mq is how much? 16 Newton per 16 to 10 power 6 Newton per millimeter divided by 4.855 into 10 power 6. Okay. Answer for this is plus 3.3. Okay. Here minus mq by zb. Mq is minus 16 into 10 power 6 divided by zb is 3.104 into 10 power 6. The corresponding answer is minus 5.15 Newton per m square. Okay. Now we have calculated all different types of stresses. Here in the problem we mentioned to calculate resultant stresses with respect to two different combination. One is a combination of prestress plus sulfate. Second is combination of prestress, sulfate and the live load. You can calculate now easily. Okay. Therefore, first question is prestress combination of prestress plus sulfate, no? Sulfate. Okay, just you add all the values corresponding to prestress and the sulfate. It is plus 2.15 minus 4 plus 1.84. I'll write the same thing here. Plus 2.15 minus 4 plus 1.84. So if you calculate the answer, almost you will get the value near to 0. Okay, here I got answer as minus 0.01, which is almost equal to 0. Okay, similarly, at bottom fiber, the resultant stress due to combination of prestress and the sulfate is 2 plus 2.15 plus 2.15, then plus 6.25, then minus 2.89. The answer is 5.51 Newton per mm square. Okay. The second combination, the second question is to calculate the resultant stress for the combination of pre-stress plus self-weight plus live load. Okay, plus live load. So here, what will be the calculation? We need to add all the numbers now. Plus 2.5 minus 4 plus 2.15 minus 4 plus 1.84, then plus 3.3 plus 3.3. The answer is 3.29 Newton per mm squared. Then here 2.15 plus 6.25 minus 2.89 and final answer the line load stress minus 5.15. Okay. So answer is plus 0.36 Newton per mm squared. Okay. So these are the resultant stress values with respect to the given combinations. Okay. To this problem is over. If you have any doubts at any point of calculation, you can ask students before moving into the next problem. Any doubts you can ask. Okay. I hope this is clear for everyone. I will move to the next problem now. Next problem. Third problem. Okay. Please go through the problem. A rectangular concrete beam 250 mm wide and 600 mm deep, the sectional dimensions are given, is prestressed by means of four 14 mm diameter high tensile bars located 200 mm from soffit of the beam. Okay, the bar details are tendon details and their location details is given. If the effective stress in the wires is 700 Newton per mm square, what is the maximum bending moment that can be applied to the section without causing the tension at the soffit of the beam? This is the question. Let me write the diagram for the data given. Solution. So it is a rectangular concrete beam. It is a rectangular concrete beam. Rectangular concrete beam. Let me write the central axis. Its dimension is 250 mm wide, 600 mm deep. 250 mm. P is equal to 250 mm and depth D is equal to 600 mm. Okay, 600 mm. So to overall depth of the rectangle is 600 mm. What will be the distance of centroid? It will be total depth divided by 2. It will be around 300 mm. Total depth divided by 2. Okay. And he says that is prestressed by means of four 14 mm diameter high tensile bars located 200 mm from the soffit. Okay. There are 4 bars. 4 bars located at a distance of 200 mm from soffit of the beam. Okay, and dia of the bar is 14 mm. Okay, the question is to find maximum bending moment that can be applied to the section without causing tension at the soffit of the beam. Okay, soffit of the beam is, okay, he says that what is the maximum bending moment that can be applied to the beam without causing tension at the soffit of the beam. Here the tension will be, the tension at the soffit of the beam should be 0. Okay, there won't be any bending stresses, or the resultant stresses should be 0 at the soffit of the beam. Okay, for that condition, what is the maximum bending moment that can be applied, that we have to find. Okay. Now, the area of the pre-stressing wires you can calculate. Okay, stress in the wires is given. Okay, pre-stress is given. Pre-stress is given. How much it is given? Pre-stress in the wires is 700 Newton per mm square. 700 Newton per mm square. So pre-stress is given, and bar details are also given. Using bar details, you can calculate the area of the bar, or area of the wires is equal to, there he says that there are 4 number of bars having dia of 14 mm. Okay, 14 mm diameter. So area of one bar will be pi into 14 square by 4. He says that 4 numbers. So by this we'll get the total area of the bar. Total area of the bar, let me calculate. Here I have not written the answer. Let me calculate. So pi d 14 mm square, no? 14 square divided by 4. There are 4 numbers into 4. So answer will be 615.75. 615.75 mm square. Okay. So stress in the wire is known. Area of cross section of the wire is known. So stress multiplied by area will give pre-stressing force in the wires. Correct? Therefore, pre-stressing force is equal to, therefore, pre-stressing force is equal to stress, that is pre-stress multiplied by area of wires. Okay, we'll give total pre-stressing force that exists in the wire arc and down. Okay, stress is how much? 700 multiplied by 615.75. Okay, therefore pre-stressing force P, how much we'll get is, check the answer. It is 431.02 into 10 power 3 Newton. This is the answer you get. Okay. So using stress in the steel and area of the steel, we have calculated pre-stressing force. Okay, this is required for the calculation. No. Now, dimensions of the rectangular section is given 250 by 600. You calculate the total area of the section, area of cross section, area of cross section. A is equal to 250 by 600. 250 into 600 is equal to, answer is 150,000 mm square. Okay, area. Then section modulus you can calculate. See, in almost all the problems, calculation of the cross section, section modulus, moment due to dead load, live load. Okay, these are all the common steps. Okay, but in this problem, it is a quite different problem. Here it is asked to find the moment. It is asked to find moment. Moment is the unknown factor here. Okay. Section modulus. Section modulus Z is equal to it is I by Y. Okay, I by Y, where I is BDQ by 12, where I is BDQ by 12 divided by Y is nothing but what? Distance of centroid from the top fiber or the bottom fiber. See, the figure is symmetric about x-axis. ZT and ZB will be same. ZT is equal to ZB is equal to Z. Okay, therefore, here Y distance of centroid is it will be 300 from bottom or 300 from the top. So it is D by 2. D by 2. So if you simplify this, BDQ by 12 into 2 by D. So answer will get Z is equal to BD square by 6. Okay. So width of the rectangle is given as 250 into depth is given as 600 square divided by 6. So the section modulus value, we check the answer, it is 15 into 10 power 6 mm cube. 15 into 10 power 6 mm cube. Okay. Then what else we need to calculate? Eccentricity we can calculate. Correct? Eccentricity. What is eccentricity? It is distance between the centroid of the whole figure to that of centroid of the prestressing force. Okay. So it is 300 minus this 200 will give eccentricity. Eccentricity is equal to eccentricity E is equal to, so 300 minus 200. So you'll get eccentricity as 100 mm. Eccentricity as 100 mm. Okay. Now coming to the question. What is the question here? What is the maximum bending moment that can be applied to the section without causing tension at the soffit of the beam? Without causing tension at the soffit of the beam means what? Resultant stresses at the bottom fiber is 0. When resultant stresses at the bottom fiber is 0, then there is no tension at the bottom fiber, correct? So you have to understand, he has given a condition that without causing tension at the soffit of the beam means tension at the soffit of the beam is 0. Tension at the soffit of the beam is 0 means the resultant stresses at the soffit of the beam is 0. Resultant stresses at the soffit of the beam is what? It is, I'll go to the introductory part. Resultant stresses at the soffit of the beam is P by A plus P by ZB minus MC by ZB minus MQ by ZB is the resultant stresses at the soffit of the beam. I will write the same formula here. I will write the same formula. Before that, we will write a sentence. Without causing tension at the soffit of the beam represents that the resultant stresses at the soffit at the soffit of the beam is 0. Soffit of the beam is 0. Therefore, P by A plus P by Z minus mg by z minus mq by z is equal to 0. Which means that the stresses due to prestressing force P by A plus P by Z should be equal to the moment that is acting on the beam. Stresses due to moment that is acting on the beam. This is what the condition, students. Okay. Without causing tension at the soffit of the beam represents the resultant stresses at the soffit of the beam is equal to 0. Okay, the resultant stresses at the soffit of the beam is nothing but P by A plus P by Z minus mg by Z minus mq by Z is equal to 0. Okay. In another way, we can understand that if the stresses caused by prestressing force is equal to the stresses caused by the moment, then there won't be any tension at the soffit of the beam. Okay. Now here it is asked to find the maximum bending moment that can be applied to the section. Maximum bending moment means that includes both mg and mq. Okay. So P by A plus P by Z is equal to maximum bending moment means that bending moment is including mg and mq. Okay. Okay, let us take this mg plus mq as z, m. Okay. Therefore, P by A plus P by Z is equal to m by z. M by z. Maximum bending moment means that bending moment is inclusive of both dead load moment and the live load moment. We will take a total moment inclusive of dead load moment and the live load moment mg plus mq as m. Okay. Mg plus mq as m. Okay. Therefore, substituting all the values, prestressing force we have calculated how much it is 431.02 into 10 power 3. 431.02 into 10 power 3 divided by cross sectional area. How much we got? 15,000. Don't substitute area of the wires. It is area of the section. 150,000. 150,000. 150,000 plus 431.02 into 10 power 3. Eccentricity we got it as 100 mm. 100 divided by Z. Section mode was how much we got? 15 to 10 power 6. 15 into 10 power 6 is equal to moment is the unknown factor. Maximum bending moment that can be applied without causing tension at the soffit. 15 into 10 power 6. Okay. Now m is only the unknown factor. If you calculate for m, that is bending moment, you will get the answer as 86.1 into 10 power 6 Newton millimeter. In terms of kilonewton meter or 86.1 kilonewton meter. Okay. With a maximum bending moment of 86.1 kilonewton meter, there won't be any stresses at the soffit of the beam. Okay, there won't be any stresses at the soffit of the beam. That is the meaning. Okay. Whenever he says resultant stresses at the soffit of the beam is 0, you need to take this condition. That's it. Okay, you need to take this condition or any top condition, the bottom equation or the top equation. Any equation you can take and you can solve for the required parameter. Okay, so this completes the problem. Any doubts you can, if you have, you can ask. Okay, let me move on to the next problem. Problem number 4. Problem number 4. Problem number 4 is a pre-stressed concrete beam of section 200 mm wide and 300 mm deep is used over an effective span of 6 meter to support an imposed load of 4 kilonewton per meter. Full point. The density of concrete is 24 kilonewton per meter cube. Okay. The sectional dimensions are given. Length of the beam is given. Lay load on the beam is given. Density of the concrete is also given. Okay. Even if it is not given, you need to assume as 24 kilonewton per meter cube only density. Then moving on, at the center of the span section of the beam, find the magnitude of concentric pre-stressing force necessary for zero fiber stresses at soffit when the beam is fully loaded. Second question is the eccentric pre-stressing force located 100 mm from the bottom of the beam, which would nullify the bottom fiber stresses due to loading. First, we will write all the given data before solving the problem. Write the diagram of the section. It is a rectangular section, 200 wide and 300 mm deep. mm wide, 300 mm deep. Okay. So if you know the dimensions, you can calculate the cross-sectional area. Cross-sectional area A is equal to 200 by 300. So we'll get 60,000 mm square. Okay. Is used over a effective span of 6 meter. Length of the beam is given as span L is equal to 6 meter. To support an imposed load of 4 kilonewton per meter, WQ is given. Lay load WQ. How much it is given? 4 kilonewton per meter. 4 kilonewton per meter. Then density of the concrete is given, correct? Yes. Density of concrete is given as 24 kilonewton per meter cube. Okay. Now we will move on to the first question. Okay, these are all the given data. What is first question? To find the magnitude of concentric pre-stressing force necessary for zero fiber stress set soffit when the beam is fully loaded. What is the meaning of concentric pre-stressing force? Let me write the diagram for the same. First question we will solve. Okay. He says that concentric pre-stressing force. The span of the beam is 6 meter. L is equal to 6 meter. L is equal to 6 meter. Live load on the beam is given. Live load on the beam is 4 kilonewton per meter. 4 kilonewton per meter. Okay. What he says? The concentric pre-stressing force necessary for zero stress at the bottom fiber. Concentric pre-stressing force means, let me write the centroidal axis for the beam. Okay. The concentric pre-stressing force means the pre-stressing force which is acting along the centroidal axis is called as concentric pre-stressing force. Remember, okay, the centroidal axis, the pre-stressing force which is acting along the centroidal axis of the beam is called as concentric pre-stressing force. Okay, if the pre-stressing force acts along the centroid, what will be the eccentricity? What will be the eccentricity? Eccentricity will be 0. Okay. What is actually the meaning of eccentricity? It is distance between centroidal axis to that of line of action of the pre-stressing force. Okay, the line of action of pre-stressing force is moving along the centroidal axis itself. There won't be any eccentricity. Okay, so the eccentricity is 0 in this case. Eccentricity is 0 in this case. Okay, and he says that we have to find magnitude of the pre-stressing force so as to cause 0 fiber stress at the socket of the beam. The condition is similar to the previous problem. What is that condition? This P by A plus PE by Z minus mg by Z minus mq by Z is equal to 0. Okay, I'll take the same condition. For getting here, you write for getting 0 fiber stress, the following condition has to be satisfied. What is that condition? Previously I explained in detail. This condition is this equation. P by A plus PE by Z. P by A plus P by Z minus mg by Z minus mq by Z is equal to 0. Or P by A plus PE by Z is equal to mg by Z plus mq by Z. Okay. So when stresses due to pre-stressing force becomes equal to stresses due to the bending moment due to dead load and the load, then resultant stress will go 0. Okay, resultant stress will go 0. That is the meaning of this modified equation. Okay, let me call this as equation number 1. Okay. Now we need to calculate pre-stressing force. Okay, P is the unknown factor here. P is the unknown factor. Area of cross section we have already calculated. It is how much? Area of cross section. Area of cross section is 150,000. Sorry, here. I should have written here. I forgot to. Let me write here that condition. Forgetting 0 fiber stress. I think I written all the fiber stress following condition. Same thing I will be writing here. Condition has to be. I forgot to write in the next problem. The previous problem only written. mg by z plus mq by z. Okay, I'll call this as equation number 1. Okay, so area of cross section P is the unknown factor. We have to find the force P, concentric pressure force. We need to find. So area of cross section we can calculate. Dimensions are given 200 by 300. Therefore, area of cross section, area of cross section A is equal to 200 by 300. That is 60,000 mm square. Then what else is it? Eccentricity is 0 with respect to this condition. Eccentricity is 0. Then section modulus Z is required. No, for Z, this formula for section modulus of rectangular section is what? In the previous problem, we know that BD square by 6 is the formula for section modulus of rectangular section, or else you can use the basic formula that is equal to I by y. You calculate the moment of inertia, you calculate the distance of centroid from the bottom or top fiber, then substituting you will get the same equation. Okay, BD square by 6. I'll directly use that formula here in the next problem. Z is equal to BD square by 6. Okay, B is 200 into 300 square by 6. So Z will be 3 into 10 power 6 mm cube. Then eccentricity is known. Section mg and mq we need to find. No, mg and mq. Mg is sulfate of the beam, moment due to sulfate of the beam. Sulfate moment. Sulfate moment mg. First you find the sulfate. Sulfate of beam equal to same steps, cross sectional area multiplied by density. Only important thing is you have to substitute the cross sectional area in terms of meter square, because density is given in terms of meter cube, kilonewton per meter cube. So the cross sectional dimensions are 200 by 300, 0.2 into 0.3, 2 into 0.3 multiplied by 24. If you do, you will get sulfate of the beam, Wg. So you will get it as 1.44 kilonewton per meter. Okay, therefore sulfate moment mg is equal to Wg L square by 8. Wg is 1.44 into length of the beam is 6 meter into 6 square by 8 into 6 square by 8. So the answer is 6.48 kilonewton meter. In terms of Newton millimeter, 6.48 into 10 power 6 Newton millimeter. Okay, mg is over, then mq moment due to live load moment, live load moment mq. So which is given by mq is equal to wq L square by 8. Live load on the beam is given how much? It is 4 kilonewton per meter. So 4 into 6 square divided by 8. 4 into 6 square by 8. Live load moment is 18 into 10 power 6 Newton millimeter. Actually, you will get 18 kilonewton meter. 18 kilonewton meter in terms of Newton millimeter. 18 into 10 power 6 Newton millimeter. Okay. So I think all the parameters we have determined. Only the unknown factor is P by A. Substitute all the values in this equation, you will get the value of prestressing force required to maintain the zero stresses at the bottom. Okay. Therefore, equation 1 becomes R Substituting, therefore, substituting all the values in equation 1, we get P by A is there, no? P by A is 60,000. P by 60,000 plus next equation is P by Z. P by Z means P into what is eccentricity? 0. Eccentricity divided by Z is 3 into 10 power 6. 3 into 10 power 6. Okay. Then is equal to mg by Z is equal to mg is 6.48 into 10 power 6 divided by 3 into 10 power 6 plus mq by Z 18 into 10 power 6 divided by 3 into 10 power 6. So in this formula, so in this equation, only P is the unknown factor that we can find. So if you find the answer, so answer will be 489.6 into 10 power 3 Newton in terms of kilonewton, 489.6 kilonewton. Okay. So the concentric force required to maintain zero fiber stresses is how much? 489.6 kilonewton. To this, the first question we have solved. Now we will solve second question. We'll solve second question. Second question, just see the eccentric prestressing force. Here it is asked to find eccentric prestressing force located 100 mm from the bottom of the beam. Okay, located 100 mm from bottom of the beam, which would nullify the fiber stresses due to loading. Okay, I'll write the diagram for the same. I'll write the centroidal axis. What is the second question? The eccentric prestressing force located 100 mm from the bottom of the beam. Okay. Overall depth of the beam is 300. Overall depth is 300. 300. It is asked to find magnitude of the eccentric prestressing force, which is located at a distance of 100 mm from the bottom of the beam. Which is located at a distance of 100 mm from bottom of the beam. Okay, this is centroidal axis. Now you can find the eccentricity of the prestressing force. What is the eccentricity of the prestressing force? The distance of centroid of the rectangle from bottom is total depth divided by 2. That is 150. Okay. Therefore, eccentricity will be equal to so distance between the centroidal axis to that of line of action of the prestressing force is called as eccentricity. That you can easily calculate now. 150 minus 100 if you do, you will get eccentricity as 50 mm. You get eccentricity as 50 mm. Okay. Now we have to find what is the magnitude of this eccentric prestressing force, which is located at a distance of 100 mm from bottom fiber, so as to cause zero fiber stresses. Okay. So as to cause zero fiber stresses. Zero fiber stresses means the same condition. The same condition right here. Or I will substitute the values in the same equation 1 with respect to second question. Okay, therefore equation 1 becomes, therefore equation 1 becomes P by A. P by A is P by 60,000 plus P by ZT. P by ZT. P into E is 50 divided by ZT or Z. That is 3 into 10 power 6. 3 into 10 power 6 is equal to the RHS term is same only 6.48 into 10 power 6. Let the same thing 6.48 into 10 power 6 divided by 3 into 10 power 6 plus 18 into 10 power 6 divided by 3 into 10 power 6. So in this LHS term, if you take the P common, then if you solve for P, the answer, the pre-stressing force is, you will get it as 244.8 into 10 power 3 Newton. In terms of kilonewton, it is 244.8 kilonewton. 244.8 kilonewton. This is what the answer we get. Okay. Only the difference between the previous, the first question and the second question is here eccentricity is 0 in the first question. In the second question, we have some eccentricity that is 50 mm. That is the difference. Calculation remains the same. Okay. So this completes the problem. Any doubts you can ask. Okay. I'll move to the next problem now. Let me strike out this so that I should not write. Okay, next problem. I think I have in one more video. Let me open that here. Problem number 5, correct? Let me open problem number 5. Yes, problem number 5. Okay, we will solve this particular problem. So we have solved 4 problems till now. We will start with problem number 5. Let's go through it. A prestressed concrete beam supports a live load of 4 kilonewton per meter for a simply supported span of 8 meter. Live load is given, length of the beam is given. The beam has I section with overall depth of 400 mm, thickness of the flange and web bar 60 and 80 mm respectively. The width of the flange is 200 mm. Beam is to be prestressed by an effective prestressing force of 235 kN. Prestressing force is given. All sectional dimensions of the I section is given. Okay. At a suitable eccentricity such that resultant stress at the soffit of the beam at the center of the span is 0. Find eccentricity required for the force. Then second question is, if the tendon is concentric, what should be the magnitude of the prestressing force for the resultant stress to be 0 at the bottom fiber of the central span section? It is also similar to the previous problem only. Okay. Let me write the data first. So the section given is I section. Okay. Let me read the sectional dimensions. The beam has I section with overall depth of 400 mm. Thickness of the flange and web are 60 and 80 mm respectively. The width of flange is 200 mm. Okay. Overall depth is 400 mm. Overall depth 400 mm. Then thickness of the flange and web are 60 and 80 mm respectively. Thickness of flange is 60 mm. Flange web is 80 mm. Thickness of web is 80 mm. So he has not specified what is the thickness of the bottom flange, top flange. He simply says that thickness of the flange is 60 mm, which that we have to understand as the thickness of both top and bottom is same only. Okay. If it is different, he would have mentioned in the problem, particularly thickness of top flange, thickness of the bottom flange. He simply says that thickness of the flange is 60 mm and width of the flange is 200 mm. Okay, which means it is similar. It is a symmetric section. Okay. Here also it is 60 mm. 60 mm. Okay. Then width of the flange, how much he said? 200 mm. Width of the flange is 200 mm. 200 mm. Here also it is 200 mm. Okay. It is a symmetric section, correct? It is a symmetric section. Let me write the centroidal axis. Centroidal axis. So no need to find the centroid. So the figure is symmetric about x-axis. Okay. If it is symmetric about x-axis, then centroid is directly total depth divided by 2. Okay, total depth divided by 2. Total depth is 400. So centroidal distance will be 200 from either side. 200 and 200. YB and YT is equal to Y is equal to 200 mm. 200 mm. Okay. It is a simply supported span of 8 meter. It is a simply supported beam. So in most of the PSC problems, we will have simply supported beam only. Okay, that is why we will use WH curve by 8 formula directly. Intensity of load given is 4 kilonewton per meter. 4 kilonewton per meter, and the span is 8 meter. Span is 8 meter. Okay. W cube is equal to 4 kilonewton per meter. L is equal to 8 meter. Okay. Then all sectional dimensions are written in the figure only. I will not write it again. Then what else we can write? Prestressing force is given. The beam is to be prestressed by an effective prestressing force of 235 kilonewton. P is equal to 235 kilonewton. In terms of Newton, it is 235 into 10 power 3 Newton. Okay, 235 into 10 power 3 Newton. At a suitable eccentricity such that resultant stress at the surface of the beam at the center of the span is 0. Same condition will come into picture again. Whatever the condition we have used for the previous two problems, no, this same condition will come here. Okay, here also it is said that in the problem, the resultant stresses at the surface of the beam at the center of the span is 0. Okay, same condition he has given. So same equation we have to use for the calculation. Okay, the question is to find the eccentricity required for the force. What is the difference between previous problem and this problem? In the previous problem, eccentricity was given. It was asked to find prestressing force. In this problem, it is reversed. Eccentricity is not given. It is asked to find the prestressing force is given. Eccentricity is not given. It is asked to find eccentricity. Okay. I'll write the same condition now for getting zero resultant stress, zero resultant stress at the bottom fiber. The following condition has to be satisfied. Has to be satisfied. What is that condition? That is P by A plus P by Z is equal to mg by Z plus mq by Z. Call this as equation number 1. Okay. P is given in the problem only. How much it is given? 235 kilonewton. 235 kilonewton. 235 into 10 power 3 Newton. Area of cross section you can calculate. Correct? Area of cross section you can calculate area. Let me join these 2 points. I'll tell you why I'm doing this. So to calculation for the calculation of moment of inertia, I'm joining these 2 points. Area I can calculate. Area, total area of the section is area of flange plus area of web. 200 by 60 plus 200 by 60 plus 80 by, what is the depth here? Here depth will be 400 minus 60 minus 60. If you do, you will get 280 mm as depth of the web portion. Okay, so 200 into 60 plus 80 into 280 plus 200 into 60. 200 into 60 plus 80 into 280 plus 200 into 60. By this we will get total cross-sectional area. That is 46,400 mm square. 46,400 mm square. Okay. Now prestressing force P is known, area is known. Okay. Eccentricity, that is only the question here. Eccentricity we need to calculate. Then Z is required, no? Section modulus Z. Z is equal to I by Y. Okay. Here figure is symmetrical about x-axis. ZV is equal to ZT is equal to Z. That is why I am taking Z. Okay. For unsymmetric section only, ZT, ZB will come into picture. Okay. For symmetric section, it is directly Z because both are equal, no? Z is equal to I by Y, where I is moment of inertia of the I section. Okay. Now you have to calculate moment of inertia I. Okay. So you can calculate moment of inertia as we have calculated in one of the previous problem. Yes, for this problem we have calculated the moment of inertia now. So you can use this particular formula. Okay. Or there is one more method. Okay. That method is applicable for only the symmetric sections. Remember, it is not applicable for the unsymmetric sections. Okay. And it is a simplest method. You can save some time in calculating this moment of inertia. Okay. So you can use this formula. This formula. Using this formula, you can calculate. Okay. Using this formula, it is applicable to all kind of symmetric or unsymmetric members. Okay. So whatever the procedure I am telling, it is applicable only for symmetric members. What I have done is I joined these 2 points. I will shade this portion. Okay. Again and again I'm telling it is applicable for only symmetric sections. Okay. Now we need to calculate moment of inertia. No. So here you calculate this distance. You calculate this distance from here to here. You calculate the distance. What will be the distance? Total is 200. Total width of the range is 200. 200 minus 80. Okay. 200 minus 80 whole divided by 2. There are 2 sides. If you do, you will get length here. So 200 minus 80 is 120 divided by 2, 60 mm. You will get 60 mm here. 60. This side also it is 60. So center it is 80. Okay. Now to calculate the moment of inertia, moment of inertia I is moment of inertia of this full area. Okay, full area mi about or moment of inertia of full area minus 2 into or let me write it that 2 in the next step minus moment of inertia of shaded area. Moment of inertia mi of shaded area. Okay, moment of inertia of the shaded area. Moment of inertia of the full area minus moment of inertia of this shaded area will give moment of inertia of this I section. Correct? So moment of inertia of full area is how much? See, the full area is it is in the form of rectangle having depth of 400, width of 200. So moment of inertia of rectangle is BDQ by 12. B is how much here? B is 200, depth is 400. 200 into 400 Q by 12 minus moment of inertia of the shaded area. Okay. First you calculate moment of inertia of any one shaded portion, any one shaded rectangle. So shaded rectangle is having width of 60, okay, and depth of 280. So 60 into 280 cube divided by 12 into 2. Why into 2? There are 2 shaded portions, 2 shaded rectangle. For one rectangle, I have calculated the moment of inertia. I have multiplied by 2. Okay. So this is nothing but 2 numbers. 2 numbers. Therefore, moment of inertia I, if you calculate, answer will be 847.15 into 10 power 6 mm4 mm raised to 4. This is the answer. You can calculate the moment of inertia using this formula also. You will get the same answer. Okay, this is simplest for the figures having symmetric symmetry. Figures having symmetry. Okay. Now we got I. We can calculate the Z now. Y is equal to D by 2. Y is equal to D by total depth divided by 2. 400 by 2 is nothing but 200 mm because it is symmetrical about x axis. So y equal to directly half of the depth. Therefore Z becomes equal to, therefore Z is equal to I by Y. Y is equal to I is 847.15 into 10 power 6 divided by Y is 200. The answer is 4.23 into 10 power 6 mm cube. 4.23 into 10 power 6 mm cube. Okay. Now you got the value of Z. What else is required? You require mc and m cube, that is moment due to self weight and the moment due to live load. Self weight moment. To calculate the self weight moment, you need the area in terms of meter square. Correct? Because density is in terms of kilometer per meter cube. Area we have calculated in terms of mm square, 46,400 mm square. 46,400 mm square. In terms of meter square, it is 46,400 into 1 mm is 10 power minus 3 m meter square. Okay. So answer is 0.0464 meter square. Here, be careful. Okay. So in a flow, what you will do is you will substitute the answer in terms of mm square. There it will go wrong. The calculation will go wrong. Be careful. Okay. Therefore, self weight of the beam W cube is equal to cross-sectional area into density. Cross-sectional area is 0.046 into density is 24. Therefore, W cube is equal to 1.11 kilonewton per meter. 0.11 kilonewton per meter. Now you can calculate the moment due to self weight. Therefore, mg is equal to WQ L square by 8, 1.11 into length. How much? 8. 8 square by 8. Answer is 8.88 kilonewton meter or 8.88 into 10 power 6 Newton millimeter. And live load moment MQ is equal to WQ L square by 8. WQ is how much? So here this is WG na. WG. Live load is given as how much? 4 kilonewton per meter. Therefore 4 into 8 square divided by 8. So answer is MQ 32 kilonewton meter or 32 into 10 power 6 Newton millimeter. Okay. Now we got all the required parameters. P, area, okay. Then Z, Mg, Mq, all the things are not just substitute in this equation. All the values you will get the required eccentricity. You will get the required eccentricity. Therefore, the equation 1 becomes, first one is P by A. P is given as how much? 235 kilonewton, 235 into 10 power 3, 235 into 10 power 3 divided by cross sectional area 46,400, 46,400, then plus PE by Z. PE by Z is 235 into 10 power 3 into E divided by Z is 4.23 into 10 power 6. 4.23 into 10 power 6 is equal to mg by z. Mg is 8.88 into 10 power 6. 8.88 into 10 power 6 divided by z is 4.23 into 10 power 6 plus mq by z. 32 into 10 power 6 divided by 4.23 into 10 power 6. So by this you will get the value of eccentricity. You can calculate the value of eccentricity. Okay. If we calculate the answer, eccentricity will be equal to 82.88 mm. 82.88 mm. To this, the first question is solved. Find the eccentricity required for the force to cause the zero eccentricity. Zero stresses, resultant stresses at the bottom table. Okay. Moving on to the second question, if the tendon is concentric, he says that if the tendon is concentric, what should be the magnitude of the prestressing force for the resultant stress to be zero? Instead of applying the prestressing force at some eccentricity, if it is applied concentrically or if it is applied with zero eccentricity, what should be the prestressing force? Question B we will solve now. Question B we will solve. If tendon is concentric, tendon is concentric. Okay. Tendon is concentric means what? There is no eccentricity. Eccentricity is zero. If eccentricity is zero, then what will be the magnitude of the prestressing force? That is the question. What will be the magnitude of the prestressing force? I will utilize the same equation. Okay. I will utilize the same equation. I will substitute eccentricity 0 because that condition is given in the second problem, second question. Okay. I will substitute eccentricity 0. I will keep P as unknown factor in this equation 1. So if I do that, it will be P by 46,400 46,400 plus PE by ZT. Eccentricity is given as 0 into 0 by 4.23 into 10 power 6. So this whole term becomes 0. Correct? Is equal to mg by z, and then you say the same term 8.88 into 10 power 6 divided by 4.23 into 10 power 6 plus 32 into 10 power 6 divided by 4.23 into 10 power 6. So by this you can work out the magnitude of the concentric force required to maintain the zero stresses at the bottom fiber. If you work out the answer, it will be 4.48 into 10 power 6 Newton. In terms of kilonewton, it will be 4.48 kilonewton. If you get, please check the answer. If you get any other answer, let me know. Okay. Any doubt in this problem? Okay. To this, we will conclude today's class and we'll continue in the next class. Okay.